Hello everyone, my name is Zaid Hassan. I will be presenting a solution to a problem which was modified in order as a problem which was in our midterm exam for the Advanced Dynamics course for Spring 2020. Now the problem that I have taken is representing motion primitives in moving frames. By motion primitives, I here mean velocity and acceleration both in linear and angular cases. Okay, so let's get into it. This is our system and we have three frames essentially: capital IJK, little I prime, J prime, K prime, and little IJK. The frame centered at O is capital IJK. It is rotating at a rate of omega 2, and we can say that it makes an angle phi 2 from its initial value. Then we have a displacement along the length L2 along the capital K direction to end up at frame A. Again, these two frames are parallel because this is just a displacement, and that L2 is a time varying length. So the derivative of L2 is constant, whereas the second derivative of L2 is 0. Then we have the frame A, and that frame at A is just little I prime, little J prime, little K prime. That frame is rotated about the little I prime axis at an angle of theta, but the rate at which it is rotated is negative theta dot, and we end up with an angle, a new frame, which is little I, little j, little k. That frame has a vector AD, and at point D we have a disk which is rotating about the little k direction, little k axis, at a rate of omega 4, and then we can assume that it makes an angle phi 4 from its initial condition. And also length L3 is constant, which is the length of the segment AD from point A to point D, whereas the length from O to A is time varying, and its second derivative is 0. So it's a constant velocity L2. Alright, what do we want to find? We want to find in the I prime, J prime, K prime frame a number of quantities. One, we want to determine the angular velocity of the disk in I prime, J prime, K prime frame. We want to determine the total angular acceleration of the disk and represent it in the I prime, J prime, K prime frame. And we want to do with the linear counterparts of these. Now before we start, it's nice to lay down a few quantities. These are the rotation matrices. We won't be using R1 and R3 per se. We will be using R2 because R1 and R3, as it turns out, we don't need them essentially. But R1 and R3, we don't need them. But R2 we will use, which is a rotation about the I prime axis of negative theta. For capital J, rotation about capital J of phi 2 is R1, and the rotation about little k of phi 4 is R3. But we will be only using R2, the second one. Okay. Now, the position and angular velocity vectors for point D and the bodies inside of this system are also important. We might want to put them out first. So the position of point A with respect to point O, as seen in the system or origin of frame at O, is just L2 capital K, which is the same as L2 K prime, because these frames are parallel. And the position vector of point D with respect to point A, as seen in frame A, is L3 sine of theta. So we have this vector projected along the K prime and the J prime, I prime, J prime, which is not shown here, and K prime axes. This turns out to be L3, the length of the segment AD, sine of theta, so the height that it takes along the J prime axis, that multiplied by J prime, and then cosine, L3 cosine of theta along the K prime axis. So pretty straightforward. And the angular velocities are, the angular velocity of frame A in the inertial is just the angular velocity about O, which is just omega 2 J capital J or omega 2 J prime. Then the angular velocity of the frame D with respect to A, or the pitching up of this arm, is minus theta dot I prime, Again, negative theta dot is just by the right hand rule because it is opposite to the direction as pointed out by the right hand rule. That is why we have a negative sign here. And lastly, we have the angular velocity of the disk about its center, which is omega 4 k, little k. Okay. Now, let's start. The first thing we want to determine is angular velocity of the disk as seen in frame A. The angular velocity of the disk at its center is omega 4 k little k hat. We can project those project that into the A frame as omega 4 sine of theta j prime plus omega 4 cosine of theta k prime. Again, this is the same as projecting AD from this tilted angle of theta to I prime, j prime, and k prime. Again, this is also the same as multiplying it by the rotation matrix that we determined previously. Now, the total angular velocity of the disk is just the angular velocity of the disk about its center plus the angular velocity of the frame A plus the angular velocity of the frame A in the inertial frame. So the angular velocity of the disk plus the angular velocity of the frame in which we projected in the about the in the A frame, and then we have the angular velocity of the frame A itself in the inertial frame, or this frame centered at O. Then we just add these three terms, and it turns out to be minus theta dot I prime. Again, that negative theta dot represents the direction is opposite to the I prime direction, and we have omega 2 plus omega 4 sine of theta along the j prime and omega 4 cosine of theta along k prime. This is pretty straightforward, just vector addition. Okay, now we want to rotate this, or we want to find the acceleration, so we will take the derivative of this. But since these are rotating frames, we use the transport theorem as well. So the derivative of the velocity of the disk does come in as it is, but there is an additional term. Let's see if we can take a highlighter from here. We see this additional term of omega prime cross omega disk in A. Now, omega disk in A is the previous thing that we determined in the last section. So this is omega disk in A, right? This is the highlighted portion. And hang on, and here we have the time derivative of whatever we found in the I prime, j prime, k prime frame, and then something cross product with it. Now this omega prime is just the angular velocity of the frame I prime, j prime, k prime. And as we know, that is just omega A in O in the inertial frame. So we plug in what we found in the previous step here, and we get d by dt of this previous value, and we get omega 2 j prime cross this previous value. And it turns out the cross product cancels out the j term, so we get a k term. J cross minus I is k, and j cross k is plus I, so we get omega 2 times omega 4 cosine of theta in the I direction. We get omega 2 theta dot in the k direction, so this term and this term. Then we have the derivative terms, which are minus theta double dot along the I direction, which was expected, and along the j direction we have omega 2 dot, and we have omega 4 dot sine of theta and omega 4 theta dot cosine of theta, which is just the derivative due to chain rule. And lastly, we have the derivative of this third term, which is omega 4 dot cosine of theta minus omega 4 theta dot sine of theta. Pretty straightforward. Okay, cool. Now let's see, we remove that. Okay, now we go to something complicated. We go to the linear velocity of point D as seen in frame A. Now, since this is going to be a little bit complicated in terms of calculation, so I will replace this image by just this frame assignment, so that everything becomes a little bit easier. Now, this is the frame assignment on the right side. It's just the same, but with the body elements removed. Now, we can recall that the position of this point A in frame at O is just L2 K prime, and the position of point D in A is just L3 sine of theta j prime plus L3 cosine of theta k prime. There should be a hat over here in L2 k prime. Then we apply the transport theorem to take the derivative of this term, which is just the sum of the position of point D is A in D, and when we take the total position of D, we get two parts, which is OA and OAD. So essentially what we get from the transport theorem is just that the velocity of D in frame A is just the rate of change of the position in position of point D in frame A plus the rate of change of position of frame A in frame O plus this transport theorem term, which is omega cross the total position vector in the inertial frame of A of point D. So we find these three terms independently. D by dt of Rd in A is just d by dt of Rd in A. This term, we take the time derivative of, now let me just pull on the highlighter again. Okay, use the laser pointer. So we take the d by dt of this term, the time derivative, which turns out to be L3 sine of theta, L3 theta dot cosine of theta, and minus L3 theta dot cosine of theta, Rd in A. And I think, yeah, we're good because there's only one term. So sine of theta has the derivative cosine of theta, theta dot. Cosine of theta has the derivative minus theta dot sine of theta. So that's what's replaced here. Then the second term is omega A in O cross Rd in A plus Ra in O. Then again we have omega A in O is just omega 2 along the j direction. We know that it's along the capital J direction. It says these are parallel. It is also along the little j prime direction. And then we plug in both of these added together. Now since j cross j is 0, we only get j cross k terms which are along the I direction, which is omega 2 times L3 cosine of theta plus omega 2 L2. And both of these will be j cross k, which is capital little I prime. Alright. And we have, let's see, the last term is d by dt of Ra and O, which is just the rate of change of this length L2. So some terms along the k direction, some terms along the I direction, and one term along the j direction. We represent them in this vector sum, or we can write them as this matrix in this matrix form. Again, the number of terms is consistent, so we have two terms here and two terms here, and we have one term here. So we should have 1, 2, 3, 4, and 5 terms in our direction. Another check could be one term in j, another in k, two in I, and the last one is also in k. So we should have two terms in the I direction, one term in the j direction, and 1 plus 1, two terms in the k direction. So we have got 2, 1, and 2. That seems nice. And then we can verify what the terms are as well. We have omega 2 L3 cosine of theta plus omega 2 L2 along I. So omega 2 L2 plus omega 2 L3 cosine of theta, that's right. Along the j direction, we have j prime direction, we have L3 theta dot cosine of theta, which is L3 theta dot cosine of theta. That is also right. And in the k direction, we have minus L3 theta dot sine of theta, minus L3 theta dot sine of theta, and L2 k prime, which is L2 k prime. So we got the same answers. We have two terms along I, one along j, and two terms along k. Right. We got the velocity of this point. Now let's go to the acceleration. In order to determine the linear acceleration, we go back to the velocity case. We have VdA as given in the previous case. Let's see. Here we have it. This velocity has 3 terms in it. So when we take the derivative, we should end up with 6 terms. And these 6 terms are these. Notice how one of the terms has a 2 right next to it, because that actually doubles. That is why we placed a 2 in this final form. So we get 5 terms, but these 3 terms have 6 independent derivatives, and 2 of them turn out to be the same. So the derivative of this term is d2 by dt2 r in d in a. So the second time derivative of this. The second derivative of this last term, the derivative of this last term is just d2 over dt2 of this d by dt, d squared by dt squared of r A and O. So just this second time derivative of these. Then this term gets a little tricky. That is omega A O cross RdA plus RA and O. This just turns out to be omega A dot. Omega dot A in O. Just the angular acceleration about the capital J direction. Now, the derivative of this multiplied by this term, and then we should get plus the derivative this term multiplied by the derivative of this term, which is exactly this omega AO cross d by dt of R d and A plus R A and O. But we get this 2 times because when we take the transport theorem, this entire thing, this V d and A, is multiplied by omega AO. So this term, this angular velocity about J, that takes a cross product with this velocity. That gives us another 2 terms in acceleration. What are those? That is omega cross this derivative plus this derivative, which is this thing, omega cross this derivative plus this derivative, right? These 2 derivatives. And that is why we have a 2 term right next to it. And the last is omega cross this entire thing. So omega cross this thing, right? This 2 times the omega cross. We get 2 omega crosses. So we get 5 terms, which was expected. The interpretation of these terms is the acceleration of point D in frame A plus the acceleration of frame A itself plus the angular acceleration times the position vector of point D in the inertial frame plus 2 times the angular velocity of frame A times the total angular velocity of point D. Now this term is a little bit tricky because it is the product of 2 velocities, but in general this is also another form of acceleration. I think it's called the Coriolis acceleration. And this last term is, or I think this term is called the Coriolis acceleration. This term is just the transport theorem of the position of the point D. Okay, cool. Now let's find these 5 terms separately. The first term is d2 by dt2 of R d and A. This, the first derivative, we take the second derivative, and this turns out to be this 2 terms along J and 2 terms along K prime. Right, then we take the second derivative of R A and O, which is just the first derivative of L2 dot K prime. Notice we found all of these terms in the previous velocity section as well, right? So we get 0 because d by dt of L2 dot is just d2 by dt2 of L2 dot L2, which is 0 because L2 changes at a constant rate, so L2 dot is constant and L2 double dot is 0, right? Then the third term, the acceleration, angular acceleration cross R d and A, that term is omega 2 dot along the J prime direction cross R d and A plus R A and O. Again, when we take the cross product, this J terms gets cancelled with J terms and we get only the cross product in the I direction. The only difference this time is instead of omega 2, we have omega 2 dot here and omega 2 dot here as well. Cool. The fourth term is 2 times omega A and O cross d by dt of R d and A plus R A and O. Again, this term is just omega 2 J prime cross product with the time derivative of this entire thing, which we know this from the previous section is just the time derivative of L sine of theta J prime plus L cosine of theta K prime, and this term is just L2 K prime. So we take the time derivative of these terms and then take the cross product. J gets cancelled with J. We end up with J prime cross K prime, which is I, and the signs are as we expect them to be. The last term is omega AO cross R d and A plus R A and O. Something important to note here there is that we perform this cross product from the right side towards the left. If we take the cross product of omega A and O with itself, we would end up with a 0 vector. That is why we don't want to proceed from the left direction. We want to go from the right direction. So this is omega 2 J prime cross R d and A plus R A and O. which turns out to be, again, this RD and A plus RA and O is just the same thing without the just the sum of the position vectors, which is R3 sine of theta j prime plus L3 sine of theta j prime plus L3 cosine of theta k prime plus L2 k prime. When we take the time derivative, when we take the cross product with j prime, the terms in j get cancelled and we get j cross k as I, and then j prime cross I turns out to be negative k. That's why we have the negative sign in there. All right. Now we have these 5 terms and we can just add them together to give the velocity of the total velocity of point D as represented in frame A. This turns out to be alpha A, D, and A is L3 theta double dot cosine of theta minus this entire thing. We have 2 terms along the j direction, then we have 1, 2, 3, 4 terms along the k direction, and 1, 2, 3, 4 terms along the I direction. So we add all of these together, or we can represent these in this single vector. Another thing to note here, if we set L2 as a constant, or this red line becomes a constant length, then L2 dot would be 0, and this term, the last term in the I direction, this thing, this goes to 0 if L2 is constant, which is similar to the solution, which is exactly the same solution we got in our exam question, because the only difference was in the exam question this L2 term was constant, whereas the problem that I'm solving here is in which L2 is actually a variable, which is a constant velocity variable. So the derivative of L2 is 0. Second derivative of L2 is 0. If we put the first derivative of L2 as 0, only this term goes to 0. And if this term goes to 0, we end up with the same solution that we had for the problem in the exam, which is a good test to know that we solved it correctly. Now, we put it all together. So these are the final or the total velocities and accelerations, both angular and linear, omega disk in A, omega alpha disk in A, V d in A, and A d in A. And these are the terms that we wanted to find. And I hope this presentation helps, and thank you for your time. Hello everyone, my name is